Alrighty, guys, can you hear me?
Yes, we can hear you.
How are you guys doing?
I'm doing pretty good.
So, hope everybody had a little break, and I think I know most of you. There are there are people that are coming in with a little bit of different backgrounds in this class. So, anyway, if you don't know me, my name is Kasper Larsen. I'm a professor at Rutgers in the math department, and we're going to be doing computational finance, and I'm gonna do my writing is going to be on these sheets of paper, and I'll post them on the Canvas site after each lecture. Compared to what I've been doing last semester, this semester is going to be a little bit different. I'm going to try to use a old-fashioned pencil because it allows me to erase. So when I make mistakes, and I always do, it'll be easy to erase. So I'm going to try to see if I can get this to work. If it doesn't work in the sense that you can't read what I'm writing, just we'll go back to the old-fashioned pen instead. But this pencil here, let's see if we can get it to work. All right, so this here is computational finance. And it's 623. So some of the rules. So what is this about? So what are the rules and the content? Well, it's going to be a lot about implementation. There's going to be a lot about implementation of models. This is we for those of you that took my class in the fall, we talked about the theory. There was very little implementation in the sense of writing code, right? So when you talk about implementation here, this means to write code. This is to write C++ code. There's always this comment here about this C++. And this is not my requirement. This is the director's requirement. This is the MF director's requirement. And it's a little bit of a tricky thing in this course because I don't know how to do this. I use MATLAB and Mathematica for my coding, but Paul Feehan, he wants the students, the MF students, to write their code in C++. So we have a TA. The TA can help with C++. So I can't help you with C++. I can help you with all the theory. I can help you with whether or not you're getting the right numbers. I can help you about how you can try to think about writing your code, but debugging your C++ code, this is not something I can do. But the TA can help. Okay, so it's going to be a lot about implementation of models. So this is a little bit tricky because at the same time as you're taking this one, you will be taking 622. Right? So we need Brownian motions. In particular, we need Dietrich's lemma from 622. So what we're going to be doing here in the beginning is we're going to wait for 622 to catch up. So here in the beginning, we will do we'll do other groundwork. And then while we're doing other groundwork, 622 is going to catch up, and you'll start talking about Brownian motion and Each's lemma and so on. And as soon as you have those under your belt, we can start using them in this class, and then we can implement models that require us to use Brownian motions and Each's lemma. Right, so what does it mean that we'll do other groundwork? Well, I mean, some of the things that we'll be doing today will be like an intro to Monte Carlo simulation. Another thing that we will be doing is we'll be revisiting these characteristic functions. We need those for some of the standard models in equity pricing. And we will also be spending quite some time talking about copulus. So these are things that will not require that we know what Brownian motions are, and you will not require us to know how to use each of them. So here in the beginning, it's going to be a little bit of a patchwork. We will like do things that are quite different, and the reason we're doing that is because we're letting 622 catch up and develop these tools that we will need to go forward. Okay, so there are office hours for help. Right, so here you should see Canvas. Let me just show you how it looks like. See if I can get this to work. Share screen. So if you go into Canvas, I'm hoping everybody can see the screen now. If you go into Canvas and you click on announcements, and then you can see there's this Zoom numbers, and you click on that one. And so here you can find all the links for the various meetings. So right now we're looking at Thursday morning. So the lecture on Thursday morning is split into two components. We will take the first part, then there'll be a break, and then you'll have to get back on a different Zoom account to do the second part. This is because Zoom creates these very large files, and breaking them up is just much easier for my computer to handle. So that's why we have two different Zoom numbers. So, so those are here. My office hours are Friday morning at 9 o'clock. And the TA, Alvin Huang's office hours, so he's the one that'll be able to help you with your C++ code in particular. His office hours are in the evenings, Thursdays and Friday evenings. And you can see the IDs and the passcodes here on Zoom. Okay, so the other things you can find on Zoom right now will be the first homework and then the syllabus. And let me just show you the syllabus. It has the one thing that you might need is to contact either me on my email, or you'll contact the TA on his email. The other thing that is useful on the syllabus is, of course, the schedule. The schedule is all the way at the back. Let me go all the way to the back. So the schedule is here. This is going to get updated as we move along, but at least in the beginning, we're going to be looking at introduction to this Monte Carlo simulation today, and then we'll move into the other things, characteristic functions and copulus. So the schedule is going to get updated as we move along. The other thing that is a bit unusual for this course compared to many of you, at least the other courses where you have seen me in, is this computational finance course has a large component that requires you guys to do a final project. So that's those descriptions are also part of the syllabus, and you can see them. They start here on page 5. It says final project description. So let me talk a little bit about that. Let me switch back to my document camera. So in this course here, there are two components. There are two components. So one is homeworks. We will have about 6. So there'll be one every other week. And then the other one, which is the new thing, this is this final report. Right, so this, there will be lots of rules spelled out on the syllabus. There's a final report, and for those of you that there's a SAS requirement that you need to have a thesis. There's a thesis requirement inside Rutgers SAS college, and this report is serving to meet that need. Right, so this is a I think I listed 6 or 7 topics on the syllabus, and so the students will choose a topic that they like and write a report on it, and that's going to be there'll be 50% here, and there'll be 50% here. We will talk a lot more about. So what I'm proposing is for you guys to read over the projects, and then there'll be a discussion. There'll be a discussion later, and so by the spring break. You need to choose. You need to pick a topic. We have 9 students in the class. If I counted correctly, we have 9 students. So these are individual. These are final, and this is an individual. These are final individual reports, and you choose a topic, and you write a 15-page report on it, and that's going to serve as a huge chunk of your grade. The homeworks and the reports, the homeworks are also individual. You're of course allowed to work together. This is fine, but you have to write up your own solutions. Don't use the solutions from other students. Actually, so there's no using old homeworks, reports. These projects that I put, the vary in level. Some of them are a bit easier, some of them are a bit more involved, some of them are a bit more practically oriented. We always have like 1 or 2 students that want to do, that are interested in doing a PhD after the program. And so I put on a few projects at the end that are more like academically interesting projects. So whatever category you fall into, you pick one of them. Are there any questions on these two parts to the overall grade? So for those of you that took 621 with me in the fall, we had all exams. We're not going to have, this is not how this class is going to be structured. Are there any questions or comments about what we have here? Okay, then what about material? So again, I put on, there are some references. There's some references on the syllabus. In general, I'll post slides and videos. Should say lectures here. Online. So there will be, for example, one thing we will do today is, so as an example, we will do this acceptance rejection algorithm. So one thing that you will need to do is you can search for this keyword. You can search for notes online, or you can use these notes that I'm going to write out here. So you can either go and buy the references that are available on the syllabus. That's a bit expensive. You can be happy enough with the slides and the videos, the lectures that we're recording, or you can go and search for the keyword acceptance and rejection algorithm. And for those of you that are sitting online right now, you can just try to key in acceptance, rejection, and there'll be lots and lots of references out there. This is also going to be needed. This here is also needed. This is needed for the projects. Right, because for the final projects, there will be some references given out. There are some references given out on the syllabus, but it will be insufficient to complete the overall project. So you will have to start searching for sources yourself if you have not already gotten used to that. Are there any questions or comments before we get started on the course? So we're gonna what we're gonna be doing now is we're gonna start looking at Monte Carlo. We're going to be looking at Monte Carlo simulation. So, okay, so so our starting point is that there exists, is that our software, is that our computer software can generate samples from a uniformly distributed from the uniform distribution. Right, so remember what the uniform distribution is. So we have a random variable, it's called u. So we have u going from omega into 0, 1. And the assumption is that this U here is uniform, you should recall that a random variable is uniform if the probability that U is less than U is equal to U for any U between 0 and 1. Right, so we have that. We have talked about that, or you should have seen that at some point in your life. Right, so the idea is, well, the starting point is that we can generate realizations of this U here. Right, so for example, if you're using Excel has a command called rand. So you call, if you're using Excel, most people have it. If you call this rand command, then your code, your computer will spit out a number as a command, which spits out, which gives out these values, we should call them U, gives out these U ends between 0 and 1. And these are realizations. These are realizations of U. Like so, they have to be thought of as this U of omega. Right, these will be UN, and then this will be omega n. And we're gonna be talking about then, given that we can simulate values of a uniform, how can we then use that to do other things? And one thing that we want to do a lot is, one thing that we've been talking a lot about is to compute these expectations. So an application would be, say you want to compute an expectation of G of U. Compute this expectation, which is, if U is uniform, so this is an integral from 0 to 1 of G of little u du. Say you want to compute this for a given function G going from 0 to 1 into R. How would one go about doing that? Well, if you want to use simulation, so if you want to use Monte Carlo simulation, then what you do is you simulate UN, some large number, and then you take the average. Of G of UN, sum them up, So that's what simulation is all about. If you wanted to compute this integral over here using simulation, and u here is uniformly distributed, you create a sequence of realizations for this random variable, you plug them in and you take the average. Just some notes. When you're looking at this expectation here, g of u, right? This thing there, this could be, it could be, this could be multidimensional. Nobody says that this is just a one-dimensional thing. You could, in principle, have as many dimensions as you want. Here's an example of this. So let's do an example. You could try to say, I want to estimate pi. Using Monte Carlo simulation. Okay, and so how would I go about doing that? Well, if I look at a square, put it here to -1, -1, 1, and 1 here. So that area of my square, this is going to be 4. And if I put a circle inside, I'm going to get pi. So I want to simulate, I want to figure out a way to simulate so I can get an estimate for what pi is. And the way I'm going to do this is I'm going to say, well, I'm going to take two uniforms, u1 and u2. They're going to be going from omega to 0, 1, and they're going to be uniform. So let these two things be independent uniforms. Remember what it means to be independent here. It means that when I'm looking at the probability that u1 is less than little u1 and u2 is less than little u2, I can calculate that probability by taking the product. That's what it means to be uniform. That's what it means to be independent, and then what it means to be uniform. So that one is this one here. Uniforms, this is provided by this equality. This is u1, u2. So we take two of these guys, they're independent, and then we look at, we transform them a little bit because we want to have something here that lives between -1 and 1. So I'm looking here at x. I need to stretch out this uniform. So I'm going to look at uniform not on 0, 1, but on -1 to 1. So I'm going to look at 2u1 -1. I'm looking at y to be 2u2 -1. So now these guys here, they're going to be independent, and they're going to be uniform on the interval -1 to 1. The joint density, the joint distribution, because they are independent, so then the joint density for x comma y is what is it? It's going to be the area of the box was 4, right? So it's going to be 1/4 for x and y between -1 and 1. Okay, so how are we gonna get closer to estimating this pi? That was the goal. We can simulate u1 and u2. We plug them into this formula, and therefore we can simulate x and y. So the ability to simulate x and y, how is that going to allow us to figure out what pi is? Well, we had this idea that the starting point was that we're going to approximate this expectation here on the left-hand side by this sum on the right-hand side. So I just need to figure out what g should be. Now g here is two-dimensional. So I want to have g of x comma y. I want to have this to be, this should be 1. This should be 1 when x squared plus y squared is less than 1. And it should be 0 else. So in that case, the expectation of g of x comma y is going to be pi over 4. And at the same time, I want to say that this here is roughly equal to, when I simulate, I'll have 1 over n, the sum of, what would it be? Column n. The expectation is going to be approximated by a sum. Inside here, I'll have g and then x. What was x? X, this was my 2u1. So this is 2u1 n minus 1. And then y was 2u2 n minus 1. Where these u1 n and u2n, DR realizations. The realizations of u1 and u2. Other questions on this? So what we do is we create these sequences. We have my function g. You take the sequences, each element is going to get squared. This one here is going to get squared. You're going to see if it's less than 1. If it's less than 1, then g here becomes a 1. If it's bigger than 1, then this g here is going to become a 0. Sum them up, take the average, and this is going to give you an estimate for pi over 4. So this is a way to estimate pi. Of course, when you do these estimates, one thing that it begs the questions, I say. So a main concern, how good is this estimate? And that's going to be the next thing that we will turn to. Any questions before we move on from this? Right, so the starting point, just to go over it one more time, the starting point for simulation, at least the starting point that we are going to take, is going to be that we have a software on our computer that can generate uniforms. And so, of course, you could go one step further back and ask, so how do I actually create uniforms? So that's a separate issue, and we're not going to get into that in this course. But the starting point for us will be that we actually can do these uniforms. We're not going to worry about how good the software that we have, how good it is to generate these uniform samples. So given that we can create these realizations, how can we use them to compute, for example, expectations? And so here was a little example with a two-dimensional object, but of course, I mean, lots of things can be used to estimate. We're also interested in how well it approximates. How well does this estimate work? And so I want to say a little bit about that. To get a handle on how well this works, we're going to be looking at confidence intervals. And I should just say here that so whenever you simulate, you need to hand these into in particular in your homework. And final project. Even though if it's not asked for, you still have to report these intervals. So I want to spend some time discussing what confidence intervals, what they are and how you compute them. Okay, so to get a handle on this, we're going to look at, so say that I have a sequence of random variables. So this is a long string, the IID, with mean and variance, mean mu, and variance sigma squared. So remember, IID, that means that you're independent and identically distributed. So I have a sequence of random variables that are IID, so they have the same mean. There is no n here on the mean and the variance coefficients. So the first thing we're going to form is the expectation. Like if we want to approximate mu, how would we do it? Well, we'll take the average. So we're going to be looking at x bar. X bar, this is going to be defined to be the average. Right, so if you look at law of large numbers, so the law of large numbers, gives that this random variable here, so we could gives us that this sum. I didn't put the capital N index on x bar. We can put that on x bar too if you want to, but law of large numbers says that this average of these independent random variables, it converges. This thing converges to mu as the number in your sum goes to infinity. We've had some discussions about, so this is a sequence of random variables, right? So there are many ways that this thing can converge. So if you want to be precise, this is P almost surely. If you are not sure what P almost surely means, and it's okay, this is not going to be a big deal in this course, but the precise statement of law of large numbers is that the average here converges to mu. It's even going to be true without the variance part here. You can just have a sequence of integrable random variables that are IID. You will have this property here. So that's the law of large numbers. This is telling you that as capital N goes to infinity, this x bar variable is going to converge to a constant, namely the mean of the individual components in the sum. Okay, you can also form the, so this is a random variable. You can take the expectation, you can take the mean, and of course you can take the variance. So if you compute, just a few things to note. If I look at the mean of x bar, so that's going to be the expectation of 1 over n, and then the sum of the xn's. Right. So here I'll use linearity of the expectation. I'll put the constant outside, and I'll put the sum outside. And then I'll have the expectation of xn. They all had expectation mu. So what I'll have here is 1 over n, the sum, and then I'll have my mu here. So how many terms in the sum? That'll be n terms in the sum. So I'll have mu times n divided by n. This here will give me mu. Right, so the expectation of this average, it's exactly, this is exactly mu, which is the same as the expectation of the individual components. So that was the mean. We can also compute the variance. So let's compute the variance. The variance of x bar. So the variance of x bar, this is 1 over n, the sum of xn, from 1 to n. Okay, so the variance, we pull out a square. We pull out a square. Like here, I'm going to use these xn's, the IID. So we're going to use here that the xn's, they are independent. These are independent. So there's no covariance that I have to take care of. Normally, when we compute the variance of a sum, the covariances are going to show up, but here the covariances, you're not there. So we don't have to worry about these covariance terms that will show up in the variance of this sum is just going to be 1 over n squared. And then the sum of the variances xn. And I can work out what this is. This is 1 over n squared. The sum of the individual variances would be sigma squared. That was our starting point. We had the expectation of xn would be mu, and the variance of xn would be sigma squared. So the sigma squared here is what comes over here. And now we have what we have. We have sigma squared times n. So we're going to end up with sigma squared divided by n. That's the variance. And in particular, the standard deviation of x bar, which is defined to be the square root of the variance, that's going to be sigma divided by root n. So here we're using that sigma is positive. If I don't have that, I'm going to get an absolute value here. We're going to play that sigma is positive. So on the previous slide, we talked about the law of large numbers. The law of large numbers has a companion, the central limit theorem. So the central limit theorem well, what does that say? Well, it says you need to take these averages. So x bar again is the average. Again, x bar is the average of the first n, capital N, xn's. Or you center it, so you subtract away its mean. The mean was mu. So you center it, and then you divide by the standard deviation. Divide by the standard deviation. This is sigma divided by square root of n. Of course, you can move this around. So this is square root n, x bar minus mu divided by sigma. What the central limit theorem says, that this thing here converges to a standard normal. This here is not standard normal. It's just assumed that the x's are IIDs. There's no assumption about normality. But the central limit theorem says that this thing here, this is approximately normal, standard normal. Remember that notation. This here is the mean. This here is the variance. This is approximately standard normal as n. This n here and that n are not the same. Like this here is the normal distribution. This here is the number as n goes to infinity. There was a little discussion about. There's a little discussion up here about what does it mean to converge. So here, the meaning over here is a little bit different. Like, what does that mean? That is approximately standard normal. Okay, so the precise statement is, and please note that this differs from the law of large numbers. Like, a precise statement is that if I take the expectation of this quantity over here, and you apply it to a function, x bar minus mu divided by sigma. So what do we need? We need a square root up there. Square root in outside there. Like if I want to compute this expectation, then this thing here is exactly equal to, when I take the limit as n goes to infinity, this is exactly, this expectation here can be computed exactly as an integral of g of x, and then you have this 1 over square root 2 pi e to the minus 1/2 x squared dx. Right, that's the precise statement. That's what it means. That's what it means for this quantity here to converge to a standard normal. So it's a bit different. It's a bit different from what we saw with the law of large numbers, where you have this convergence p almost surely. That's not the kind of convergence you will have for law of large numbers. So this here is true for any g continuous and bounded. So what we're going to be using is, we're not going to be looking at the limit. We're going to be using this idea that for capital N being sufficiently big, you are approximately normal in this sense here. And that's what we're going to be using to create these confidence intervals. Questions so far? You guys are very quiet. You are more than welcome to interrupt and ask questions throughout the lectures. Questions about what we're talking about here?
So, Professor, have you given us the formal definition of the confidence interval?
Not yet. Not yet. We are working towards it. Okay. We're working. We're getting there. We're just, what we're doing is we're setting up like the underlying like random variables and notation and so on. That's coming up next. Okay, so so the message here is the message here is that for any common distribution, these xn's, for any common distribution of these xn's, like for xn, where these guys, they are the IID, no matter how that common distribution is, when I'm looking at the average, we're looking here at the average. This is my x bar. This quantity here, centered, the variable, this one here, which is not normal, right? Because it has whatever crazy distribution. This random variable here, centered, so I should say properly centered. The word center is important because it goes here from the central, so it has the center stuff. Properly centered, so this is x bar minus its mean divided by its standard deviation. So this is your sigma divided by square root of n. Properly centered, this is approximately standard normal. And the word approximately is in this sense up here with this function g. The miracle is that you take any distribution, it doesn't matter how crazy it is. You do this trick and you're going to get a standard normal. So towards the very end of our class in the fall, the 6-1 class, we were thinking about maybe looking at the passage from discrete time to continuous time. So we were looking at these binomial models throughout the entire course. And that would have fit in here, right? You would have had the stock price or the returns in these discrete time models. You would have a distribution that was very different from the normal. In that class, where there were up and down coin flips, and yet, even in such a model, you would have this standard approximate normal distribution. I posted these notes. Maybe we can have a quick look at them just to see how it would look like. So I'll post these notes on this course too, because not all of you had access to the material from last year. But for those of you that did, you can find them there, but we just find the ones from Steve Shreve. He wrote a chapter on this. Black-Scholes, where did it go? Yeah, this one here. So I'll post this set of notes by Steve. And there's a discussion here of the law of large numbers, which we've talked about now here again. And then he moves into the central limit theorem. That's this one here, which was the second part. And he has an example where he talks about like how does the binomial model converge to the Black-Scholes model. And you can see here that he's trying to illustrate what does it mean to be this approximate normal on a picture, and he's looking at like a 25-period binomial model and how does it compare to a Black-Scholes model. And just looking at these pictures, you can get a sense of, yeah, it really does seem to become standard normal. Like the bell curve is the one that we had on the piece of paper. The Gauss function e to the minus 1/2 x squared. That is exactly the solid line that you're seeing, and then the histogram. This is what you're getting out of the binomial model, right? So the standard normal density, that was what we had just on the previous slide. This bell curve. So I'll post these notes here also on this slide, and you can see there the precise statement of the central limit and the law of large numbers. And then the last part here was what I wanted to do in the end of 6-1, but we ran out of time. We didn't do the Black-Scholes convergence. I'll post these notes here later today, and you can grab them there. But the miracle thing is that you take any distribution, it doesn't matter what it is, as long as it has a finite mean and a variance, and then you get this standard normal out in the limit. Okay, enough said about that. As one of you asked about, so can you please tell me what the confidence interval is? And yeah, so that's what's coming now. So what is the confidence interval about? Well, so first of all, you need to settle on a number, and the standard number to settle on is a 95% confidence interval. You'll see where that number shows up in the calculations. So a standard 95% confidence interval is standard. So let me do that one. This 95% confidence interval. So what is that? Well, you take a random variable. You take a random variable. It's called z. It's a standard normal. For such a random variable, for a standard normally distributed random variable z, the probability that z sits between minus 1.96 and 1.96 Anybody knows what that number is? So the picture is, this is my density function. This is my 1 over, what was it, root 2 pi e to the minus x squared divided by 2. And I'm now looking at the interval from minus 1.96. And here is 1.96. If I compute the mass sitting in here, how much mass do I get? Well, this is where the 95% comes in. This here is equal to 0.95. So that's a property of the standard normal distribution. So if you were to increase this to a different number, if you wanted to put 90% here, if you wanted to put 99% here, this number 1.96, this would have to change. Okay, so we're going to be using this. So for because x bar minus this mu divided by sigma times square root of n is approximately standard normal. That's like Z. What we have is, because this is approximately standard normal, we will have that the probability that minus 1.96, this is less than x bar minus mu divided by sigma square root of n. This is not exactly 0.95 because it's only approximately standard normal. So this here is approximately 0.95. And then we can rearrange this quantity here. What I can do is I can rearrange this to say what would be x bar and then minus 1.96 times sigma divided by square root of n. This is less than mu, this is less than x bar plus 1.96 sigma, and this should be a square root, right? This should be a square root. That this is approximately 0.95. Right, so that's the confidence interval. We call this x bar plus minus 1.96 times sigma divided by square root of n. We call this the 95% confidence interval. So when you estimate, this average here is something that comes out of your estimate. And then what you need to report is whatever estimate it is plus that correction term over here. And if you are moving into a different confidence interval, if you're moving away from this 95%, then you'll have to change this 1.96 here. So often there is a there's a complication. So often you face an obstacle. You face this particular obstacle. Often you face the problem of not knowing sigma, right? You need that sigma of here, sigma divided by square root of n. So you don't know this in advance. Then it's hard to report it. So then what that means is so you also need to estimate the standard deviation. So that is what we're going to move into now. So this confidence interval, this is really nice. What it requires, I mean, of course, you know what capital N is because that's how many samples you're running. But what you don't know is this sigma here. So that's part of the problem. How do you estimate that? So let me talk a little bit about this, right? So at this point we have x bar. This is 1 over n. And then the xi's. So now we're playing the game that you actually don't know what these ones are, so you have to be estimated as well. Like x bar is what estimates mu, so what estimates sigma squared? Well, that's going to be what we'll call s squared. So how do we get a handle on s squared? Well, we'll correct the formula up here a little bit. And then you have your xi, and then you'll have minus x bar squared. And then there's a debuggle, like what are we going to put out in front? Should it be 1 over n, or should it be 1 over n minus 1? And if this is the first time you see it, this here is not a typo. This is not a typo. And why is this not a typo? Well, let's look at a little claim here that will explain why this is not a typo. The claim is, so this is of course going to be a random variable because xi is a random variable and x bar is a random variable. The claim is that if I take the expectation of s squared, I'm going to get exactly the sigma squared. This estimate here has the right expectation. And this is where you need this n minus 1. If you just put n here, this won't work. If you put 1 over n minus 1, this is going to work. And the proof is not bad. You just write out what the expectation is. So let's work out on that sum. All right, so I'm taking the sum here, and I'm going to square it out. Going to factor out the square. So this will be x I. I should put an I on n here, so put an n maybe. This is wrong all the place. This n and that I should be the same. Okay, so we get the square comes in, this becomes a square there. And I get 2x in x bar squared. Okay, so now I'll move the sum in on each term. This will be xn squared minus so what will I get here? I'll get 2 x bar, and then I'll have the sum of the xn's. So we write that. And then over here I'll have n times x bar, right? Because there's no little independence on the last term. And this part here, this one here, this is equal to, this will be equal to capital N times x bar. And if I sum up these xn's, I will get capital N times x bar. So I have minus 2 of them, and I have plus 1 here. I can cancel them out and get something that looks like xn squared. I have the same term, that's minus 2, so I'm going to get minus n x bar squared. Okay. So now I know what this sum here is, so I can work out what is the expectation of s squared. Well, if I look at the expectation of s squared, I can move the bottom factor over on the other side. So I'll get here n minus 1. So then I take the expectation of this term. So I'll take the expectation of this term on the left-hand side, xn minus x bar squared. And then I'll use what I just calculated, take this term, stick it in there, use linearity. This will be the sum and the expectation of xn squared minus, and then the n times the expectation of x bar squared. Okay, so we have to work out these second moments, but this is not so bad because we know a lot about them. We're just going to use, just recall up here that the variance of a random variable a can be calculated as the expectation of a squared minus the expectation of a squared. And here we're interested in these second moments, and we can express the second moment in terms of the variance and the first moment squared. Okay, so this here is the second moment of the xn's. The second moment of the xn's is going to be equal to the variance plus the first moment squared. The variance is equal to the expectation, that's the second moment, minus the first moment squared. That's what I plugged in here, and I'll do the same thing for the other term. This is going to be minus an n, and then it's going to be the variance of x bar plus the expectation of x bar squared. And all that we worked out before, this here is independent of n, it's the IID, so we get an n here. Now the variance of the individual x's, that was given to be far back. The variance of the individual x's was given to be sigma squared. So I'll take that sigma squared and put it in here. Plus, and the means the means were given to be mu. So I'll put that in here, mu squared. And then over on the other side, we have minus n. Then we have the variance of x bar. Okay, we figured out what that was somewhere. The variance of x bar, this was sigma squared divided by n. Plus, and then the mean of x bar squared, we also calculated that somewhere. The mean, the expectation of x bar was mu. So I'm going to get a mu squared here. And so what we see now is I'll have sigma squared times n minus 1. And then I'll have n mu squared minus n mu squared. They cancel out. And so it won't, mu squared is going to drop out here. And we have this expectation is exactly sigma squared. And you see, it won't work if I would have put an n here, because I'll have n minus 1 over here. So that was another calculation that just shows page what? Page 11, 12. All this shows is you have to normalize here by n minus 1 if you want to have this property that the expectation is exactly sigma squared. Right, so when sigma is not known in advance, you will replace sigma by this quantity here. Any questions on this? There's an interesting side comment. Just this is just a note. It's interesting for many. It's useful, and it also comes with quite a story. If you look up the name is Gosset, Gosset. Look up Gosset's student T distribution. So student T distribution. And the interesting part is it has to do with Guineas. With Guineas beer. I'm sure some of you have come across the Guinness beer, and the story that's following now is it has to do with Gosset, who worked for Guinness, and he created a distribution called the student T distribution, and he published under this Gosset name only came later. He didn't publish under his own name. And it had to do with this, his job was working for a beer factory while he was doing student T distribution. So what's the student T? So this is the note. So when these xn's are normals, when the I are these standard normals, when the I are these standard normals, well then this x bar, which is a linear combination, this is also going to be normal. Linear combination of normals will also be normal. So that's going to imply that if I center it, x bar minus mu divided by sigma over root n, this is also normal. Right, but that's when sigma is here. So the estimate was, however, when you replace s squared, when you replace sigma by that s we had before, by this guy up here. So when you replace sigma in this formula by the square root when you replace sigma by this s here, the sampled standard deviation, right? So you're going to consider here, instead of x bar minus mu over sigma root n, you will consider, and you consider this x bar minus mu, and then here you'll have, instead of sigma, you'll have your s, and then divided by square root of n. This quantity here is not going to be standard normal anymore. Now you're looking at a ratio, but this is standard normal, but you're dividing here by this mess over here. And what you want to get is a, and consider this quantity. This is not normal, but it's a student t, but a student t with n minus 1 degrees of freedom. Right, so when you had the sigma, this ratio here would be standard normal. If you switch it to a setting where you don't know what sigma is, so you have to use this empirical standard deviation, then you're outside the standard normal case. That means that when you go back and look at these intervals, there's going to be sometimes, at least, you'll see a different term. So sometimes you see this x bar, right? What was it? Plus minus 1.96, and then it was, what was the formula we had? Right, this was our formula, right? We had x bar plus minus 1.96 sigma divided by square root of n. Sometimes you'll see this times sigma divided by square root of n. Right? Sometimes you see this replaced by and then you have this x bar plus minus, and then instead of this 1.96, you'll see this t, and then it'll be alpha divided by 2, and then it's really n minus 1, and then you'll have your sigma root n. Sometimes you'll see that, right? And this, the reason for this funny notation is this 1.96. This thing here is often written as a z, and then it's this alpha divided by 2, right? And alpha is the confidence level. Right, alpha is 5%. So we should just, there's just, one could try to compare these quantities. Like, so for alpha equal to 5%, and let's compare these quantities. So we look at n-1 being, say, 20. So then this t, what is that t? T of alpha divided by 2, and then n-1. I looked it up. This becomes 2.09, right? So it's different than 1.96. But if you go down, you could try to do n-1 being or maybe 30. Then TO alpha. Or maybe I should call these just n. Just call these n. Right, so this here will be 19. This one here would be 29, and that would be like 2.045. If I go down to 60, T alpha over 2, then you have 60, so that'll be 59. Maybe this is 60 plus 1. This would be 2, and if I did 100, T alpha over 2 with 100, this would be 1.984. So you can see as n increases, this coefficient that might appear, it's going to get closer and closer to 1.96. Like, and for us, n is 1,000,000. So this distinction between using a student t distribution instead of the standard normal, it's not really relevant, because when the sample size get to be so large, the coefficient you get out from the student t is the same as what you get out from the standard normal. So this distinction here is, it's really just a note. It is, however, real that when you do these calculations, knowing sigma, this is something that you simply just, you don't know what mu is and you don't know what sigma is. So we have to get it out from the sample. But whether or not you should use 1.96, so you should go through the effort of figuring out what these t values are, this is much less relevant. Okay, other questions? Other questions on what we've been doing? If not, let's take a little break and try to get back here around 10 o'clock. So if you're not used to it, you have to go on a different Zoom link, and then we'll get back together here around 10 o'clock for the last part of the lecture. Okay, I'll see you in a little bit.